Cloud cover in the North Atlantic reaches up to 70%, often hiding the sun for days. Yet Viking sailors crossed thousands of kilometers without compasses. How did they navigate? In this video, we explore the science behind Viking sunstones and polarized light. If you enjoy clear, research-based content, consider subscribing, liking, and sharing.
Welcome to the channel. You are watching Wonders of Innovation.
Part 1. The problem of a hidden sun. Imagine sailing across a freezing ocean more than 1,000 years ago. There is no GPS, no compass, and no accurate map. Around you, there is only dark water, floating ice, and a sky covered with thick gray clouds. The wind is strong, the air is cold, and your survival depends on knowing one simple thing: direction. This was the reality of the Vikings. Between the 9th and 11th centuries, Norse sailors traveled across the North Atlantic Ocean. They reached Iceland, Greenland, and even parts of North America. These journeys often covered more than 2,000 kilometers across open sea. Modern researchers agree that such navigation required consistent direction over many days. But here is the problem. In the Arctic and North Atlantic regions, the sun is often hidden. Scientific data shows that cloud cover in these regions can reach up to 70% of the time. Fog, snow, and storms can block the sky for days. During these moments, the sun disappears completely. There are no shadows, no clear light source, and no visual reference. For most sailors, this would mean getting lost. Navigation at sea depends heavily on the sun. At midday, the sun helps identify south. At sunrise and sunset, it shows east and west. Without it, direction becomes uncertain. Even small errors can lead to large mistakes. A deviation of just 5 degrees can shift a ship by hundreds of kilometers over a long journey. So how did the Vikings manage this challenge? Historical texts offer a strange clue. In a medieval Icelandic story called Rolf's A with a cute TTR, a king watches as a man uses a sunstone to locate the sun behind clouds. He holds the stone up to the sky and somehow identifies the hidden position of the sun. For many years, historians thought this was only a myth. But modern science suggests otherwise. Researchers began studying a crystal known as Iceland spar. This mineral, found in Iceland, is a clear form of calcite. It has a unique optical property called birefringence, or double refraction. When you look through it, you see 2 images instead of one. At first, this effect seems simple, even strange. But it reveals something deeper about light. Even when the sun is hidden, sunlight still reaches Earth. It enters the atmosphere and scatters in all directions. During this process, the light becomes partially polarized. This means the light waves begin to vibrate in specific directions instead of random ones. This pattern is not visible to human eyes. However, it carries information. The direction of polarization depends on the position of the sun. Scientists have measured that the strongest polarization appears about 90 degrees away from the sun's location. This creates a predictable pattern across the sky, even when clouds block direct sunlight. In other words, the sky still contains a hidden map of the sun's position. The question is whether the Vikings could read this map. Modern experiments suggest they could. When polarized light passes through Iceland spar, it splits into 2 rays. The brightness of these rays changes depending on the angle of the crystal. By rotating the crystal and observing these changes, it is possible to estimate the direction of the sun. In controlled studies, this method can achieve accuracy within a few degrees. That level of precision is enough for ocean navigation. This idea changes how we see Viking technology. They may not have had advanced instruments, but they understood natural patterns. Through observation, experience, and simple tools, they may have used the physics of light to guide their journeys. The sun was hidden, but not lost. And the sky, even under clouds, still pointed the way forward.
Viking ships could travel about 15 kilometers per hour in good winds. Over a week, they covered more than 1500 kilometers. Without direction, even a small mistake could lead far off course. This shows navigation was not optional. It was critical for survival, trade, and expansion across the North Atlantic in harsh conditions.
Part 2. The physics of polarized light explained simply. The key to understanding Viking sunstones begins with light itself. Light may seem simple, but it carries hidden structure. To understand how Vikings could find the sun behind clouds, we must first understand how light behaves in the sky. Light travels in waves. These waves move forward, but they also vibrate. In normal sunlight, these vibrations happen in many directions at once. This type of light is called unpolarized light. When sunlight enters Earth's atmosphere, it interacts with air molecules. These molecules are tiny, but they affect light in an important way. As sunlight hits them, it scatters. This process is known as Rayleigh scattering, and it is the reason the sky appears blue. But scattering does more than change color. It also changes the direction of light vibrations. Instead of vibrating randomly, scattered light begins to vibrate in more organized directions. This creates polarized light. The amount and direction of polarization depend on the position of the sun in the sky. Even if the sun is hidden behind clouds, this polarization pattern still exists. Think of it like footprints left behind. You cannot see the person, but you can still follow their path. Scientists have measured how this works. The strongest polarization occurs at about 90 degrees from the sun's position. This means if you look at the sky at the correct angle, the light there will carry the strongest directional signal. Across the sky, this creates a pattern. At some points, polarization is weak. At others, it is strong. The direction of vibration also changes smoothly across the sky. Together, these variations form a map that points back to the sun. Humans cannot see this pattern directly. However, some animals can. Bees, for example, use polarization patterns to navigate. Even when the sun is hidden, they can still find direction using this invisible signal. This shows that polarization is reliable enough for navigation. Now the question becomes, how can a human detect it? This is where crystals like Iceland spar become important. Iceland spar has a special structure. When polarized light enters it, the crystal splits the light into two separate rays. These rays are called the ordinary ray and the extraordinary ray. Each ray responds differently to the direction of light vibration. Because of this, the two rays do not have the same brightness. If the incoming light is strongly polarized, one image may appear brighter than the other. If the polarization changes, the brightness difference also changes. This is the key observation. By rotating the crystal and watching how the brightness shifts, a person can detect the direction of polarization in the sky. And since polarization depends on the sun's position, this gives a way to locate the hidden sun. Modern experiments confirm this idea. In controlled conditions, researchers used Iceland spar under cloudy skies. By carefully rotating the crystal, they could estimate the sun's direction with an average error of less than 5 degrees. In some cases, accuracy improved to about 2 degrees. For ocean travel, this level of precision is very useful. A navigator does not need perfect accuracy. They only need a consistent direction. Even small corrections each day can keep a ship on course across long distances. This explains how Vikings could sail even when the sun was not visible. They were not guessing. They were reading patterns in light. Without knowing the scientific terms, they may have learned through practice. By observing the sky and testing crystals, they could build a reliable method over time. This is an important idea. Science does not always begin with equations. Sometimes it begins with careful observation and repeated experience. The Vikings lived close to nature. they watched the sky every day. Over years, they may have noticed that certain crystals revealed something hidden. What looked like magic was actually physics. Polarized light turned the cloudy sky into a guide. And with the right tool, even an invisible sun could still be found.
Polarized light was first scientifically described in the 17th century, long after the Viking Age. Yet Vikings may have used it practically centuries earlier. Studies show polarization can remain detectable even under 90% cloud cover. This means the sky still carries directional signals, even when it looks completely uniform to human eyes.
Part 3: Iceland Spar and the Science of Double Refraction. To understand how Viking sunstones worked, we must look closely at the material itself. The most likely candidate for the legendary sunstone is a crystal called Iceland spar. This mineral is a clear form of calcite, found in large deposits in Iceland and other northern regions. At first glance, Iceland spar looks like ordinary glass. It is transparent, smooth, and colorless. But when you place it over text or an object, something unusual happens. You do not see one image. You see two. This effect is called double refraction. In scientific terms, it is known as birefringence. It occurs when a material splits incoming light into two separate rays. These rays travel at different speeds and take slightly different paths through the crystal. As a result, a single point becomes two images. This is not an illusion. It is a direct result of the internal structure of the crystal. Inside Iceland spar, atoms are arranged in a specific pattern. This structure interacts with light in a directional way. When light enters the crystal, it does not behave the same in all directions. Instead, it separates into two components. These components are called the ordinary ray and the extraordinary ray. The ordinary ray follows the normal laws of refraction. The extraordinary ray behaves differently, bending at a different angle depending on the crystal's orientation. Because of this, the two rays exit the crystal at slightly different positions. This creates the double image effect. But this is not just a visual curiosity. It is the key to detecting polarization. Each of the two rays responds differently to polarized light. When light enters the crystal, its vibration direction determines how much energy goes into each ray. If the light is polarized in one direction, one image may appear bright while the other appears dim. If the polarization changes, the brightness of the images also changes. This gives us a powerful tool. By comparing the brightness of the two images, we can learn about the polarization of the incoming light. And since polarization depends on the sun's position, we can use this information to find the sun. The process is simple in principle. A navigator holds the crystal up to the sky and looks through it. They observe the two images formed by the crystal. Then they slowly rotate the crystal. As the crystal rotates, the brightness of the two images changes. At certain angles, the images may appear equally bright. At other angles, one becomes clearly brighter than the other. The point where the brightness balances is important. This position reveals the direction of polarization. By repeating this observation in different parts of the sky, the navigator can estimate where the sun must be located. Modern scientists have tested this method in detail. Experiments show that even under thick cloud cover, polarization patterns remain detectable. Iceland spar can reveal these patterns with high sensitivity. In some studies, trained users achieved directional accuracy within 2 to 5 degrees. This level of precision is enough to maintain a steady course at sea. For example, if a ship travels at 10 km per hour, a 5-degree error over 10 hours results in a shift of less than 10 km. This is manageable, especially if corrections are made regularly. The effectiveness of Iceland spar depends on its quality. Clear crystals produce sharper double images. Impurities can reduce accuracy. Large crystals are easier to use because they provide a wider field of view. Archaeological evidence supports this idea. A piece of calcite crystal was discovered in a shipwreck near the island of Alderney, dating to the 16th century. Although this is later than the Viking Age, it shows that such crystals were used in navigation even after the magnetic compass became common. This suggests continuity of knowledge. The Vikings may have been among the first to use birefringent crystals for navigation. Their understanding was practical, not theoretical. They did not need to know the physics. They only needed to know what worked. This is a powerful reminder. Advanced knowledge does not always require advanced language. Sometimes, careful observation and simple tools are enough to unlock the hidden patterns of nature. And in the case of Iceland's spar, those patterns could guide a ship across an ocean.
Iceland's spar can split light with high precision, creating two clear images even in low light. Its birefringence is among the strongest in natural crystals. This makes it especially useful for detecting small changes in light direction. Such sensitivity allows it to reveal patterns that are otherwise invisible without instruments or modern technology.
Part 4: Reconstructing the Viking Method Step by Step. Now that we understand polarized light and Iceland spar, we can reconstruct how a Viking navigator might have actually used a sunstone at sea. This is not guesswork alone. Modern researchers have recreated the method through experiments, combining physics, history, and practical testing. Let us imagine a Viking sailor standing on the deck of a ship. The sky is fully covered with clouds. There are no shadows, and the sun cannot be seen directly. The ocean moves constantly, making observation more difficult. Despite these conditions, the navigator begins the process. First, they take a crystal, likely Iceland spar, and hold it up toward the sky. The crystal must be clean and clear enough to produce two visible images. The navigator looks through it, focusing on a patch of sky rather than a specific object. At this point, the crystal shows two overlapping images of the sky. Next comes the key step. The navigator slowly rotates the crystal. As the crystal turns, the brightness of the two images changes. One image may become brighter while the other becomes dimmer. This change is not random. It depends on the polarization direction of the incoming light. The navigator carefully watches this change. At a certain angle, both images appear equally bright. This balance point is important. It indicates that the crystal is aligned in a specific way relative to the polarized light. This is the first measurement. But one observation is not enough. To improve accuracy, the navigator repeats the process while looking at different parts of the sky. Each observation gives a line of possible sun positions. When these lines are combined, they intersect at a point. That point is the estimated position of the hidden sun. Modern studies show that using 2 or 3 measurements can significantly improve accuracy. With practice, a navigator could perform this process quickly, even on a moving ship. Time is also important. The sun moves across the sky at about 15 degrees per hour. This means the navigator must update their estimate regularly. By repeating measurements every few hours, they can maintain a reliable direction. Once the sun's position is known, the navigator can determine direction. For example, at local midday in the northern hemisphere, the sun is generally toward the south. By knowing this, the navigator can orient the ship accordingly. Even outside midday, the sun's path provides enough information to estimate east and west. This method does not require perfect precision. It requires consistency. Small errors can be corrected over time. If the navigator checks direction multiple times a day, they can keep the ship on a steady course. Researchers have tested this exact method in real environments. In one study, participants used Iceland spar under cloudy and even twilight conditions. The results showed that trained users could estimate the sun's direction with an average error of about 3 to 5 degrees. Even in challenging light conditions, accuracy remained useful. Another important factor is human skill. The method depends on careful observation. The navigator must recognize subtle changes in brightness. This skill improves with experience. Over time, a skilled navigator could make faster and more accurate judgments. This suggests that Viking navigation was not just about tools. It was about training. Young sailors likely learned by watching experienced navigators. They practiced reading the sky, using crystals, and checking direction regularly. This knowledge was passed down through generations. There is also evidence that Vikings combined multiple methods. They may have used the Sunstone along with other cues, such as wind direction, wave patterns, bird movement, and coastline knowledge. Together, these methods created a reliable navigation system. The Sunstone was one part of a larger strategy. What makes this remarkable is the simplicity of the tool. A single crystal, used correctly, could reveal hidden information in the sky. It turned invisible patterns into visible signals. This was not magic. It was applied physics. And through this method, Viking sailors could cross vast oceans, even when the sun itself was completely hidden from view.
Modern reconstructions show that taking 3 measurements instead of 1 can reduce directional error by nearly 50%. This suggests Viking navigators may have repeated observations for better accuracy. Simple repetition improves results. This method shows an early form of practical problem solving, similar to basic scientific measurement techniques used today.
Part 5: Experimental Evidence and Modern Scientific Testing. For many years, the idea of Viking sunstones remained uncertain. Some historians believed the stories were symbolic rather than practical. However, in the late 20th and early 21st centuries, scientists began testing the concept using controlled experiments. Their goal was simple. Could a crystal like Iceland spar really help locate the sun when it is hidden behind clouds? To answer this, researchers designed experiments that recreated real navigation conditions. They used natural sunlight, artificial sky models, and even outdoor tests in cloudy weather. The results provided strong evidence that the method works. One important experiment involved measuring how accurately people could find the sun using polarized light. Participants were given birefringent crystals and asked to estimate the sun's position under overcast skies. They rotated the crystals, observed brightness changes, and recorded their results. These estimates were then compared with the actual position of the sun. The findings were impressive. In many cases, participants achieved accuracy within 5 degrees. With practice, some improved to around 2 degrees. This level of precision is more than enough for ocean navigation, especially when measurements are repeated throughout the day. Another study focused on the limits of the method. Researchers tested the technique under different weather conditions, including thick cloud cover and low sunlight angles. They found that polarization patterns remain detectable even when the sky appears completely gray. However, accuracy decreases in certain situations. For example, near sunrise and sunset, the polarization pattern becomes weaker and more complex. In these cases, errors can increase. Despite this, the method still provides useful directional information. Scientists also tested different types of crystals. Iceland spar performed best due to its strong birefringence and clarity. Other materials, such as quartz, showed weaker effects and were less reliable. This supports the idea that Vikings likely selected specific crystals for navigation. In addition to laboratory experiments, field tests were conducted. Researchers went outdoors with crystals and attempted to locate the sun in real time. These tests included conditions similar to those faced by Viking sailors, such as moving environments and changing weather. The results confirmed that the method works outside the lab. Even in dynamic conditions, trained users could estimate direction with reasonable accuracy. This suggests that the technique was practical, not just theoretical. Another important piece of evidence comes from archaeology. In 1971, a shipwreck was discovered near Alderney in the English Channel. Among the objects recovered was a piece of calcite crystal. Although this ship dates to the 16th century, long after the Viking Age, it shows that such crystals were used in navigation even when magnetic compasses were already available. This raises an interesting question. Why would sailors continue using crystals if compasses existed? The answer lies in reliability. Magnetic compasses can be affected by local magnetic disturbances, especially near iron-rich rocks or during solar activity. In contrast, a sunstone relies on light, not magnetism. This makes it a useful backup tool. Modern navigation systems often use multiple methods for the same reason. Redundancy increases safety. The Viking approach may have followed a similar principle. By combining sunstones with environmental knowledge, they reduced the risk of getting lost. Scientific modeling has also helped confirm the idea. Computer simulations of sky polarization patterns show that the sun's position can be reconstructed using measurements from multiple points. These models match the results of real-world experiments. This alignment between theory and observation strengthens the case. It shows that the method is consistent with known physics. Overall, the evidence suggests that Viking sunstones were not mythical objects. They were practical tools based on real optical principles. While we cannot prove exactly how every navigator used them, the scientific data supports their effectiveness. This changes how we view early navigation. It shows that advanced understanding does not always require modern technology. With careful observation, simple materials, and repeated practice, it is possible to solve complex problems. The Vikings may not have written equations or conducted formal experiments, but their methods align closely with modern science. And their success at sea suggests that their understanding was both deep and reliable.
In controlled studies, trained users improved accuracy after just a few hours of practice. This shows the method is learnable, not random. Some experiments report success rate above 80% in cloudy conditions. This level of reliability is enough for consistent navigation, especially when combined with regular corrections during long sea journeys.
Part 6: Limits, Errors, and Real-World Challenges. While the Viking Sunstone method is impressive, it is not perfect. Like all navigation techniques, it has limits. Understanding these limits helps us see how Vikings may have adapted their methods in real conditions. The first challenge is weather. Although polarization patterns remain visible under clouds, extremely thick or layered clouds can weaken the signal. When clouds scatter light multiple times, the polarization becomes less clear. This makes it harder to detect precise brightness differences in the crystal. Rain and snow also reduce visibility. Water droplets scatter light in many directions, which can reduce polarization contrast. In heavy storms, the sky may become too uniform for accurate readings. In such cases, the sunstone method becomes less reliable. Another limitation is time of day. Near sunrise and sunset, the sun is low on the horizon. At these angles, polarization patterns become more complex and less predictable. The maximum polarization no longer forms a simple pattern. This increases the chance of error. Studies show that accuracy can decrease significantly during these times. Instead of errors of 2 to 5 degrees, mistakes may increase to 10 degrees or more. Over long distances, this could lead to noticeable drift in direction. Human factors also play a role. The method depends on careful observation. The navigator must judge when two images appear equally bright. This is not always easy. Small differences in perception can lead to incorrect conclusions. Fatigue makes this worse. After hours at sea, in cold conditions, a navigator's ability to detect subtle changes may decrease. This introduces additional uncertainty into measurements. The movement of the ship is another challenge. A Viking ship does not remain stable. Waves cause constant motion. This makes it harder to hold the crystal steady and observe small brightness differences. Even slight movement can affect accuracy. To manage this, navigators likely took multiple readings. Instead of relying on a single observation, they could average several measurements. This reduces random errors and improves reliability over time. Crystal quality also matters. Not all Iceland spar is perfect. Some crystals contain impurities or internal flaws. These can distort the double image or reduce clarity. A poor quality crystal would make it harder to detect polarization accurately. This suggests that Vikings may have selected and preserved high-quality stones carefully. There is also the issue of calibration. The navigator must understand how the crystal behaves. This requires practice. Without training, it is easy to misinterpret the brightness patterns. Over time, experienced navigators would develop a sense of how the crystal responds under different conditions. Environmental factors add complexity. In polar regions, ice and snow reflect light. This reflected light can interfere with polarization patterns in the sky. The result is a more complicated signal that requires careful interpretation. Despite these challenges, the method remains useful. The key is not perfection, but consistency. If a navigator makes small errors but checks direction regularly, they can correct their course. For example, a 5-degree error over a few hours may not matter if adjustments are made later. This is similar to modern navigation. Even today, systems like GPS are checked and updated continuously. No single measurement is trusted completely. Instead, multiple data points are combined over time. The Vikings likely used a similar approach. They did not rely only on the Sunstone. They combined it with other observations, such as wind direction, ocean currents, bird behavior, and coastline features. This combination reduced risk. If one method failed, others could support it. Research simulations support this idea. When sunstone measurements are combined with periodic corrections, navigation accuracy improves significantly. Even with occasional large errors, overall direction remains stable. This shows that the method is robust. It can tolerate mistakes and still function effectively. In conclusion, the Viking Sunstone was not a perfect tool. It had limits, errors, and challenges. But when used skillfully and combined with other knowledge, it became a powerful navigation aid. It allowed sailors to move forward with confidence, even when the sky offered no clear guidance. And in the uncertain conditions of the North Atlantic, that ability made all the difference.
Computer models show that even with occasional large errors, overall navigation remains stable if corrections are made every few hours. This means the system is tolerant to mistake. Vikings did not need perfect readings. They needed frequent updates. This approach is similar to modern navigation systems that rely on continuous adjustments rather than single measurements.
Part 7. Combining Sunstones with Traditional Viking Navigation. The Viking Sunstone was powerful, but it was never used alone. Viking navigation was a complete system built from many different observations. The Sunstone was one important tool within a larger set of skills. To understand how Vikings traveled so far, we must look at how they combined different methods. First, consider the sea itself. Experienced sailors can read wave patterns. In the North Atlantic, waves often follow consistent directions based on prevailing winds. Even when winds change, long ocean swells can continue in the same direction for many hours or even days. By observing wave direction, Vikings could estimate their course. This method is still used today in basic navigation training. Wind was another important factor. Vikings understood seasonal wind patterns. In certain times of the year, winds blow more consistently in specific directions. By combining wind direction with wave patterns, sailors could confirm their heading. Bird behavior also provided useful clues. Seabirds tend to stay within certain distances of land. For example, some birds rarely travel more than 100 kilometers away from shore. If sailors saw increasing numbers of birds, it could indicate that land was nearby. Different species also gave different signals. Some birds returned to land at night. By watching their flight direction in the evening, sailors could estimate where land was located. Cloud patterns offered additional information. Clouds sometimes form over land due to differences in temperature and moisture. These cloud formations can remain stable and visible from a distance. Skilled observers could recognize these patterns and use them as indirect signs of land. Smell was even used as a navigation tool. Near coastlines, the air can carry scents from vegetation or soil. Although subtle, experienced sailors could notice these changes. All of these methods worked together. But they had limits. Waves can change. Winds can shift. Birds may not always be present. Clouds can be misleading. None of these methods alone is completely reliable. This is where the sunstone becomes especially valuable. Unlike waves or birds, the polarization pattern in the sky depends directly on the sun's position. Even under clouds, this pattern remains relatively stable. This makes the sunstone a consistent reference point. By using the sunstone, Vikings could determine the sun's direction. Then they could compare this with other observations. If wave direction matched the expected course based on the sun, confidence increased. If there was a mismatch, the navigator could investigate further and adjust. This process is similar to cross-checking in modern navigation. Multiple independent sources of information are compared. Agreement between them increases reliability. Another important concept is dead reckoning. This method involves estimating position based on speed, time, and direction traveled. Vikings likely used this technique as well. They could estimate how far they had traveled each day and adjust their expectations accordingly. However, dead reckoning accumulates error over time. Small mistakes grow larger with distance. The Sunstone helps reduce this problem. By providing regular directional checks, it allows navigators to correct their course. This keeps accumulated error under control. Modern simulations support this combined approach. When sunstone measurements are used together with environmental cues, navigation accuracy improves significantly. Even if each method has some error, their combination creates a more reliable system. This reflects an important principle. Complex problems are often solved using multiple simple tools. The Vikings did not rely on a single invention. They built a system based on observation, experience, and adaptation. Training was essential. Young sailors likely learned these skills over many years. They observed experienced navigators, practiced interpreting signals, and gradually developed confidence. This knowledge was practical. It did not require written instructions or scientific theory. It was learned through doing. The Sunstone fits perfectly into this system. It adds a stable, physics-based reference to a set of environmental observations. Together, these methods allowed Vikings to travel across vast and dangerous oceans. They did not need perfect certainty. They needed enough reliable information to keep moving in the right direction. And by combining tools like the Sunstone with traditional navigation skills, they achieved exactly that.
Ocean swells can travel thousands of kilometers without changing direction. This gives sailors a long-term reference even when winds shift. By combining swell direction with sunstone readings, Vikings could confirm their path. Using multiple natural signals together increases accuracy and reduces risks, creating a more reliable navigation system over long distances.
Part 8. Archaeological Evidence and Historical Debate. The idea of Viking sunstones is fascinating, but an important question remains. Do we have real evidence that Vikings actually used these crystals for navigation? To answer this, we must look at both archaeology and historical records. Unlike ships or weapons, navigation tools are rarely preserved well over time. Materials like wood, leather, or small handheld objects can decay or be lost. This makes direct evidence difficult to find. However, there are some important discoveries. One of the most discussed findings comes from a shipwreck discovered near the island of Alderney in the English Channel. This wreck dates to the 16th century, long after the Viking Age. Among the recovered objects was a clear calcite crystal, identified as Iceland spar. This discovery is significant. It shows that sailors were still carrying birefringent crystals even after the magnetic compass had become widely used in Europe. This suggests that such crystals had practical value in navigation. While this does not directly prove Viking use, it supports the idea that the method was known and useful. Historical texts provide additional clues. The most famous reference comes from an Icelandic manuscript known as Ralsei with a QTTR. In this story, a character uses a sunstone to locate the position of the sun behind clouds. The description is brief, but it matches what we now understand about polarization and crystal optics. Some scholars argue that this text is symbolic or fictional. Medieval stories often include magical or exaggerated elements. However, others point out that many historical texts mix real knowledge with storytelling. Practical techniques can be preserved in narrative form. There are also indirect references. Other Norse texts describe the importance of observing the sun, sky, and environment for navigation. While they do not mention crystals directly, they show that Vikings paid close attention to natural signals. The absence of frequent references to sunstones may have a simple explanation. If the method was common knowledge among navigators, it may not have been considered special enough to describe in detail. Everyday tools are often less documented than rare or ceremonial objects. Modern researchers have debated this topic for decades. Some scientists strongly support the sunstone hypothesis, pointing to experimental evidence and historical hints. Others remain cautious, noting the lack of direct archaeological proof from the Viking period itself. This debate is part of normal scientific process. Evidence must be tested, compared, and questioned. In recent years, the balance of evidence has shifted. Experimental results consistently show that sunstones can work as navigation tools. Archaeological finds, although limited, demonstrate that such crystals were used by sailors. Historical texts provide at least one clear reference. Together, these pieces form a coherent picture. It may not be complete, but it is consistent. Another important factor is trade. Vikings had access to Iceland spar through their settlements in Iceland. This means the material was available to them. Transporting a small crystal would be easy, and its durability makes it suitable for repeated use. This strengthens the argument. The tool was available, useful, and supported by indirect evidence. Some researchers have also explored alternative materials. Cordierite and tourmaline are other crystals that can detect polarization. However, Iceland spar remains the most effective due to its strong birefringence and clarity. This makes it the most likely candidate for the historical sunstone. Even without definitive proof, the idea has gained wide acceptance in scientific and educational discussions. It represents a plausible and well-supported explanation for how Vikings navigated under cloudy skies. The debate continues, but it has become more focused. Instead of asking whether the method is possible, researchers now explore how often it was used and how it was combined with other techniques. This shift is important. It shows that the concept has moved from speculation to serious study. In conclusion, the evidence for Viking sunstones is not based on a single discovery. It is built from multiple sources. Archaeology, historical texts, and scientific experiments all contribute to the picture. While some uncertainty remains, the overall conclusion is clear. The idea is grounded in real physics and practical possibility, and it offers a compelling explanation for one of history's most impressive navigation achievements.
Only a small number of navigation tools survive from ancient times, making direct evidence rare. However, trade routes between Norway and Iceland ensured access to useful materials like calcite. This supports the idea that Vikings had both the resources and opportunity to develop such tools, even if physical evidence remains limited today.
Part 9. What this reveals about Viking knowledge and science. The story of Viking sunstones is not only about navigation. It also reveals something deeper about how knowledge develops. It shows that advanced understanding does not always begin with formal science. Sometimes, it begins with observation, experience, and careful attention to nature. The Vikings did not have written theories of optics. They did not describe polarization, wave behavior, or birefringence in scientific terms. Yet their actions suggest that they understood these effects in a practical way. This type of knowledge is often called empirical knowledge. It is based on repeated experience rather than formal explanation. For example, a navigator may notice that when a certain crystal is rotated, the brightness of light changes. Over time, they may connect this change with the position of the sun. They may not know why it happens, but they know that it works. This is the foundation of many early technologies. Agriculture, medicine, and navigation all developed this way. People observed patterns, tested ideas, and kept what was useful. In the case of the Vikings, the environment played a major role. The North Atlantic is one of the most challenging regions for navigation. Weather conditions change quickly. Visibility is often poor. Ice, fog, and storms create constant uncertainty. To survive in this environment, sailors needed reliable methods. This pressure likely encouraged innovation. When traditional methods failed, such as direct observation of the sun, new solutions were needed. The use of sunstones may have emerged from this need. Another important factor is culture. Viking society valued exploration and travel. Trade routes, raids, and settlement required long-distance sea journeys. This created a strong incentive to improve navigation skills. Knowledge was also shared within communities. Experienced sailors taught younger ones. Techniques were passed down through practice rather than written instruction. This allowed useful methods to spread and improve over time. The sunstone fits into this system as a learned skill. It requires practice to use effectively. The navigator must recognize subtle changes in brightness and understand how to interpret them. This suggests that sunstone use was not random, but part of a trained tradition. Modern science helps us understand what the Vikings were doing. By studying light and crystals, we can explain the physical principles behind their method. This does not reduce their achievement. Instead, it highlights it. They discovered a working solution without formal theory. This challenges a common assumption. We often think that advanced knowledge depends on modern science. But history shows that practical solutions can exist long before theoretical explanations. The Vikings were not scientists in the modern sense. But they were careful observers. They paid attention to patterns in the sky, sea, and environment. They tested ideas through experience. Over time, they built a system that allowed them to navigate across vast distances. Their success is measurable. They reached Iceland around the late 9th century. Greenland was settled in the 10th century. Evidence suggests that Norse explorers reached North America, known as Vinland, around the year 1000. These journeys required consistent navigation over open ocean. Small errors could lead to failure. The fact that these voyages succeeded repeatedly suggests that their methods were reliable. The Sunstone may have been one of the key tools that made this possible. It represents a bridge between observation and science. It shows how natural phenomena can be used in practical ways, even without full understanding. Today, we use advanced instruments to navigate. GPS systems rely on satellites and precise timing. Compasses use magnetic fields. Modern ships combine multiple technologies for accuracy and safety. Yet the underlying idea remains the same. Navigation depends on reading signals from the environment. The Vikings used the sky itself as their guide. Through simple tools and careful observation, they accessed information that was invisible to the human eye. This is what makes the Sunstone so important. It is not just a tool. It is an example of human ingenuity. It shows how curiosity, experience, and attention to detail can lead to powerful solutions. And it reminds us that knowledge can take many forms, even in the absence of formal science.
Human learning often follows a pattern of trial and error. Repeated success reinforces useful methods. Over generations, this creates reliable knowledge without written science. Viking navigation likely evolved this way. Their success in reaching distant lands suggests a system refined over time, proving that practical experience can produce highly effective solutions.
Part 10: Legacy, Modern Relevance, and Final Understanding. The story of Viking Sunstones does not end in the past. It continues to influence how we think about navigation, science, and human innovation today. What began as a practical solution for survival at sea has become an important example in modern research and education. One of the most important lessons from the Sunstone is the value of simple tools. In a world filled with advanced technology, it is easy to assume that only complex systems can solve difficult problems. However, the Sunstone shows that simple materials, used with skill and understanding, can provide powerful results. This idea is still relevant. Modern engineers often design backup systems that do not rely on electricity or digital signals. For example, pilots and sailors are trained to navigate using basic tools in case advanced systems fail. This ensures safety in unexpected situations. The Sunstone fits perfectly into this concept. It does not depend on batteries, magnets, or mechanical parts. It relies only on natural light and human observation. This makes it highly reliable under certain conditions. Researchers today continue to study polarization navigation. Some modern sensors are inspired by the same principles. These devices detect polarized light to determine direction. They are used in robotics, drones, and even space exploration. For example, scientists are exploring polarization-based navigation systems for autonomous vehicles. In environments where GPS signals are weak or unavailable, such as underwater or on other planets, polarization patterns could provide an alternative method of orientation. This shows that the idea behind the Sunstone is not outdated. It is being adapted and improved using modern technology. Another important area of research involves animal navigation. Many species use polarization patterns to find direction. Bees, ants, and some birds can detect polarized light and use it to navigate. By studying these animals, scientists gain insights into efficient navigation strategies. The Viking Sunstone represents a human version of this natural ability. It acts as a bridge between human technology and biological systems. Education is another area where the Sunstone has value. It provides a clear example of how physics applies to real-world problems. Concepts like polarization and birefringence can seem abstract, but the Sunstone connects them to a practical use. This makes it a useful teaching tool. Students can see how scientific principles relate to history and everyday life. The Sunstone also changes how we view the Vikings. They are often remembered as warriors or explorers. While this is true, their achievements in navigation show a different side. They were careful observers and skilled problem solvers. Their success was not based on luck. It was based on knowledge. Even without written theories, they developed methods that align closely with modern scientific understanding. This highlights the importance of experience and observation in the development of knowledge. The broader message is clear. Innovation does not always require advanced technology. It requires curiosity, attention, and persistence. The Vikings faced one of the most difficult navigation environments in the world. Instead of giving up, they found ways to adapt. They used the tools available to them and learned from the natural world around them. The Sunstone is a symbol of this approach. It represents the ability to find hidden patterns and use them effectively. Today, we continue to build on similar ideas. We use science to understand the world more deeply, but the foundation remains the same. Observation leads to insight, and insight leads to innovation. In conclusion, the Viking Sunstone is more than a historical curiosity. It is a demonstration of applied physics, human ingenuity, and practical problem solving. It shows how invisible patterns in nature can become powerful tools when understood correctly. The Vikings may not have known the scientific terms, but they understood the results. And through that understanding, they were able to navigate vast oceans, even when the sun itself was completely hidden from view.
Modern navigation failures still occur when systems depend on a single method. This is why redundancy is important. The Viking approach naturally included backup strategies. By combining tools and observations, they reduced risk. This principle is still used today in aviation and maritime systems, showing that their methods remain relevant even now.